We will talk now about logical clocks, which a notion of clock that captures causality. We remember the happen before relation, and the happen before relation says 2-3 things. First thing, if two events happen on the same node and one happens before each, the second one means that A happens before B on the same process, then we say that A causally precedes B. If A is an event that produces a message M, and B is a delivery event for M, then we say that A happens before B. If A is a delivery event of a message and B is an event that consumes the message, then we say that A happens before B, and they are the relation is transitive. If neither A happens before B or B happens before A, we say that these events are concurrent. We have seen this before. So now we want to be able to locally tell if two events are causally related. We do this by a notion of a clock or logical time. We call it Lamport clock. So Lamport clock is a logical time. It's basically implemented by a counter, and this counter tries to capture the causality between events. So each process has a local logical clock. So it's kept in the variable t, and it's initially 0. And whenever, and this is updated, we will see now the rules for update. But whenever a process sends a message, so it piggybacks the value of the logical clock and the process identifier on that message. Okay. So when an event happens, we have two cases. If the event is a local event on a process, so we increment the logical clock by 1. And if the event is a reception of a message from a process Q, then we compare our local time t, local clock, and the local clock attached with the message. We take the max out of these two and we increment by 1 to update our local counter that is Lamport clock. How to compare Lamport clocks? We can have a total order on Lamport clocks or two timestamps by using the Lamport clock and the process ID as a pair for comparison. And we do comparison based on lexicographic order, which says basically if T sub B and with P is less than T sub Q and Q, if either T sub B is less than T sub Q, or in case they are equal, then the process identifier of P is less than the process identifier of Q, considered as numbers. So we break ties using node identifiers or process identifiers. So you can see here is an example. So this timestamp is less than this timestamp because 5 is less than 7. And this timestamp here is less than this one because even the timestamps, the logical clocks are equal. The process ID of P2 is less than the process ID of P3. Okay, so what properties we have with Lamport clocks? The property that we have is the following. If an event A happens before an event B, then we can guarantee that the timestamp associated with event A is less than the timestamp associated with event B. And you can see this from the way these counters corresponding to Lamport clocks are incremented. In case we run on one process P, this is a local event, it has a time t, say 5. When it performs another local event, say t prime, so the clock is incremented to 6. So the time stamp associated with this event, call it event B, is greater than the timestamp associated with this event, which is A. Now if we have another process Q and we send a message here, and we assume now that the latest timestamp associated with the latest event on Q, say it is 4. So at this point here, when we get the message, we compare 6 with 4, we take the max of it, and we increment that by 1, so we get a timestamp 7. So we can see that this was a reception of a message sent by process P, and the timestamp associated with this delivery of the message, as you can see here, is higher. So really we can see that the time stamps associated with the events reflect the causality. So this is the property that I just mentioned, which Lamport timestamp guarantee that if A happens before B, then the timestamp associated with A is less than the timestamp associated with B. Now we can go one step and see an example. Here's an example of Lamport clocks. We start by this is a space time diagram that we have seen before. The clocks are initialized to 0. We perform an event here at P1, so the clock is incremented by 1. Then we perform another event at P1, so we increment the logical clock by 1. Another event here, so this is we have now 2. Here we increment the logical clock by 1. 3. We send 3 on the message, and then here we compare the timestamp of P2, which is 0, with 3. 3 is max of 3, so we have max 3 and 0, and then we add 1, so we get a logical timestamp here is 4, and so on. So this is the timestamp here is 1. We can see that if the events are not related, we cannot say so much about the timestamp associated with the events. So these, for example, 2 events that are concurrent and the timestamp associated with them is arbitrary, basically. You can see here that, so this is, they were concurrent, one is higher than the other, this one is higher than this one. If we continue here, the timestamp 6, and here we have 7. This again is concurrent with the timestamp of this one. So nothing, if the events are concurrent, we cannot use Lamport timestamps. All right. Now we continue with vector timestamps after we studied Lamport timestamp. We know from Lamport timestamps is that if A happens before B, then we know that the T associated with A is less than the time associated with B. But if we have TA less than TB, we cannot say anything, which we mean that we cannot guarantee, if we have 2 events and one precedes the other, that we cannot guarantee that if we have 2 timestamps and we want to know if one of the event precedes the other, we cannot do this using Lamport timestamp. So we have to use another notion. And the notion we use is vector timestamps, which will guarantee that if it's a vector clock, it's very special, it will tell us if we look to the timestamp associated with two events, we can tell which one happens before the other, and also we can tell if these events are concurrent or not. Okay, and that notion is called vector timestamp. So in vector timestamp, we have a vector associated with each node. This vector has number of elements equal the number of nodes in our system, and element number I is associated with events happening at pi. Okay. All right. So how vector timestamp work? So each process P has a local vector, the size of n, as I said, and initially all the fields, all the elements are initialized to 0. And whenever we send a message, we add the vector of that process with the message. Okay, so we piggyback VP on every message sent. Now, for each event or transition, we update the local vector clock as follows. This is our local events, local event. For a local event, we look to the field associated with P, and we increment that field by 1. And if we have a delivery event of a message, so that means that we have a vector associated with the message. We call this vector VQ. Then we compare element-wise the local vector VP with VQ, and we take the max of that, and we update the local vector. Okay. This means now what we really get is an updated vector which knows the events, at least a count of the events that happened that process Q knew before. You can see this here. Okay. So let us look again to how we compare now vector clocks. Vector clocks can be compared with each other, but the comparison is a partial order, which means some vectors cannot be compared with other vectors, and we will see this clearly here. We say that one vector is less or equal to the other vector if each element in vector P is less or equal each element in vector Q. Okay, each element. And VP is strictly less than VQ in the case that some of the elements are the same, but for some elements in VP they are strictly less than the corresponding elements in VQ. If this is not true, that what I mean by that, if it's neither the case that VP is less or equal VQ, nor VP is less or equal VQ is less or equal VP, then we say that the two events are concurrent. The two events associated with these vectors are concurrent. So here is some examples. Here is two vectors for three processes. We say we have the value 1, 2, 3, 2, 3, 4. This is clearly that this vector is less than that one. Now if we have a vector where we know 1, 3, say 1, and here's 3, 1, 1, these two vectors cannot be compared. Cannot be compared. So if this is associated with an event A and this is associated with event P, we say that these two events are concurrent. Okay. Here is, of course, the properties that we get. We get the property of Lamport clocks, but we get also the other property, which telling us that if VP is less than VQ, if we just look to the vectors and associated with event A and event B, and we see that one is less than the other, then we know that event A happened before event B. Here's an example, and we will run this example as follows. So here is a case where we increment now the local element. It's incremented here for P1. We perform another event on P1. So we increment its local element again. Another event. And now we send a message. Here we send a message. And this message now, this is interesting to see what happened to the vector after the delivery of the message. The message has the vectors 3, 0, 0. So the new vector at this point says will be 3, 1, because one event happened at P2 and 0. This is an interesting information just to understand intuitively. This is saying at this point I know that 3 events happened on P1 and 1 event happened on P2, but I know nothing about P3. Okay, and this is a continuation of the example, as you can see. So with vector timestamp, we can actually now compare events and say if they are concurrent or not. Here's an example of concurrent events. These are 2 vectors associated with the events that are not comparable. So these can be considered concurrent events. These are concurrent. So vector timestamp is actually quite powerful. It can, just by looking at the vectors associated with the events, can tell us which events are causally related, which ones are concurrent. But there is one important result maybe you should know, is that it is not possible to implement vector timestamps with vector less than n. The size of the vector cannot be less than n for n nodes. So this is a known result. This is tell us that if we have very large number of nodes in our system, maybe sending around a vector with, say, thousands of elements could be an overhead. But okay. So now we have seen 2 notions of clocks: Lamport clock and vector timestamps. And here is some question for you. So the question is, which one of the clocks are define a partial order and which one defines a total order? So we have the relation happened before. The question, is it a partial order or a total order? We have the relation on Lamport timestamps, and we have the relation on vector timestamps. So I would like you to answer this question. And now I leave it for a second. And here is the answer. The happened before is a partial order relationship because it does not order concurrent event. The Lamport logical clock is a total order because we break the ties using process or node IDs. So any 2 clocks can be compared. But it doesn't tell us so much, right? These clocks. It's just it is the other way. If it only tells us if we know that if the events are partially ordered, we know that the timestamps should be related, that one precedes the other. Whereas with vector timestamps, we know it's a partial order, and we know that concurrent events are not ordered. I will end this. Here is just by a reminder. Logical clock gives us the following property. If A happens before B, we know that the timestamp associated with A is less than the timestamp associated with B, if it happens before. And in vector clocks, we know the both directions. We know that as in logical clocks, but we know also that if we look to the timestamps and one is less than the other, then we know that A happens before B. Now I will end this by leaving a question to you. Which of these are more important properties? Is it property 1 or property 2? I'll leave it for you to answer. Okay. Here's another question. What extra information do vector clock give us?